Hey, what's up guys, this is Rohan here. So diffusion models are a new class of state-of-the-art generative models that generate diverse high-resolution images. They have already attracted a lot of attention after OpenAI, Nvidia and Google managed to train large-scale models, and the results from them have been pure magic. Example architectures that are based on diffusion models are Glide, DALL-E 2, Imagine, and the full open source everybody's love affair, the Stable Diffusion. There are already a bunch of different diffusion based architecture. Here I will focus on the most prominent one, which is the denoising diffusion probabilistic model, or DDPMs. Fundamentally, diffusion models work by destroying training data through the successive addition of Gaussian noise and then learning to recover the data by reversing the noising process. After training, we can use the diffusion model to generate data by simply passing randomly sampled noise through the learned denoising process. More specifically, a diffusion model is a latent variable model which maps to the latent space using a fixed Markov chain. Ultimately, the image is asymptotically transformed to pure Gaussian noise. The goal of training a diffusion model is to learn the reverse process. So now talking about the training, a diffusion model is trained by finding the reverse Markov transition that maximizes the likelihood of the training data. In practice, that means that the training consists of minimizing the variational upper bound of the negative log likelihood. Combined with text-to-image guidance, these models can be used to create near infinite variety of images from text alone by conditioning the image generation process. Inputs from embedding like clip can guide the seeds to provide powerful text-to-image capabilities. With these models, we can do image generation, image denoising, inpainting, outpainting, just to name a few. And what about the diffusion models that makes them so strikingly different from their predecessor? The simplest answer to that question is their ability to generate highly realistic imagery and match the distribution of real images better than GANs, or generative adversarial network. Also, diffusion models are more stable than GANs because GANs are subject to mode collapse, where they only represent a few modes of the true distribution of data after training. This mode collapse means that in the extreme case, only a single image would be returned from any prompt given to a GAN model. Diffusion models avoid these problems this problem as the diffusion process smoothens out the distribution, resulting in diffusion models having much more diversity in imagery compared to GANs, or generative adversarial network. So diffusion models also can be conditioned on a wide variety of inputs such as text-to-image generation, bounding boxes for layout to image generation, masked images for inpainting, and lower resolution images or super resolution. Alright, that pretty much wraps about this video. If you liked it, do smash the like button, and also don't forget to subscribe. See you in the next one, and thank you very much for watching.